Right, we're going to talk about section 5.4, optimization, applications of every mathematical thing you've ever learned ever. In some ways, this is the culmination of 12 years or 10 years or whatever of your education in math, leading up to this, which, as I mentioned previously, I think section 5.4 and 5.6 are essentially all word problems. We're going to spend 1 week about approximately on this section called optimization. So what we're trying to do is, well, I think it's probably best to just do some examples so you can see, but we'll be optimizing. We'll be trying to find optimum values, maximum values, minimum values in the context of real world problems. Although the first couple we will start off with are fairly, they're applications of calculus, but they're just like more abstract. All right. Here's the strategy you want to have in your mind as you approach these problems. Okay. Number one, you want to take a second to understand the problem. Now, this might seem obvious. Of course, you want to understand the problem, but I really mean take a second, think about what's the problem asking, what type of values am I looking for, what type of equations would I expect to be using, what kind of a diagram would be useful, if a diagram would be useful, or a picture. Just try to think about, should your answer be positive or negative? What's a good range for your answer? Just think about what's going on in the problem before you just crash into it. There's a situation where a lot of the problems are different. It is not like, in maybe Algebra 2 where you learn a thing, you practice that thing a bunch of times, and then you've got problems that apply that very thing. This is different. This is a culmination of a lot of stuff put together here, all loosely around applying differential calculus. So take a second, understand what's going on in the problem, and then you want to develop some sort of mathematical model and include pictures along with it if the problem warrants some sort of picture or diagram. Okay, graph the function if your calculator is allowed, and if that's the case, these are almost like pre-calculus problems if you can use your calculator, because you'll get your model and you'll graph it and then you'll analyze it, right? Just something you do in pre-calc and algebra 2. Then if you can't, though, then you're going to find critical points, and then you're going to interpret the meaning of the critical points in the context of the problem. So for instance, if you expect your answer to be between 0 and 50, and you get a critical point -15, that's probably something that you throw away. It's probably an artifact of the abstractness of the math and not relevant to the problem that you're doing. Okay, and then interpret your solution, which means make sure you understand your solution in the context of the problem. Use units, proper units as well. Okay, so let's get started here. First one, find two numbers whose sum is 20 and whose product is as large as possible. So you want two numbers. You call those numbers whatever you want. I'm probably going to use x and y. You could use a and b, whatever you want. But I'm just going to write that the two numbers have to sum to be 20, and there's no restrictions on whether they can be positive or negative. Okay, so I've got one equation. It's just going to be this: x plus y equals 20. Okay, and then we want to find and whose product is as large as possible. So that means we want the product, maybe we'll just call that P, to be as large as possible. And the product is x times y. Okay? So what we're trying to do here is maximize P. Okay? So to do that, we've got two equations, two unknowns, and we want to solve this one for either x or y and plug it in here. For simplicity's sake, so that I can call this function P of x, I'm going to just solve for x and solve for y and drop that expression into P. So y is equal to 20 minus x. And we'll take this and drop it in here, and then I'll get my function that will optimize or maximize the product. So P of x is going to be equal to x times x, 20 minus x. All right, and then this one is not difficult to do by hand, so we'll just do it real quick. So this is going to be P of x is going to be 20x minus x squared. P prime then is going to be equal to 20 minus 2x. And if you set that equal to 0 and solve, you get x equals 10. Okay, now that's obviously half your answer. Again, thinking about this from the beginning, you're looking for two numbers, right? So then to figure out what y is, you would just plug this into x plus y, and you'd figure out that y has to be 10 as well. Okay, so some of these are going to feel very much like pre-calc type problems. Okay, let's do another one. This one you should try on your own. If we were in class, I'd have you try it, and then I would have you try it, and then we'd go through it together. You should pause the video, give it a try, and then play the video, all right? Find two numbers whose difference is 30 and whose product is as small as possible. So here, the thing that we're trying to optimize, or minimize in this case, is the product, okay? So find two numbers whose difference is 30. So that means that x minus y, or y minus x, whichever you want to do. I guess we'll go y minus x. Y minus x is equal to 30, because that's how we did it last year. So y minus x is equal to 30, and also we are trying to optimize the product. So again, minimize the product, x, y, okay? So we'll do a very similar thing. I'm going to solve for y here. I'll add x to the other side, so I'll get 30 plus x, and the function that I'll be trying to minimize is p of x is equal to 30 plus x times y. No, I'm sorry, x times 30 plus x. Okay, and then let's use our graphing calculator to solve this one. Okay, so we'll pop this into Desmos real quick. We don't even need to simplify it necessarily, so we will just go x times x minus 30 plus 30, excuse me. Turn on projector mode here. Okay, we can't really see what's going on, so let's squeeze it on the y-axis here, see if we can't figure out. Okay, so here's our minimum over here. So our minimum turns out to be negative 15, and that might be confusing because our previous question was a positive number, but there's no restrictions on x or y, or either of the numbers that is, being positive or negative. So negative 15 is fine. So x equals negative 15. That's one of our numbers. And then to figure out what our other number is, we can just plug it in here. So y plus 15 equals 30. That's going to result in y being equal to positive 15. Okay. And so that's it for that one. Let's go on to number 3. Now here's where we start to get to the real application problems. Okay. Maximize the volume of a box with an open top. Suppose we have a 20 by 25 inch sheet of tin. We want to cut squares out of each corner of the sheet and fold up the sides to create a box. How large should the squares be to maximize the volume of the box? I can't remember, it varies from year to year whether we do a problem like this in pre-calc, but I suspect you've done something similar to this. This is a situation where we really want to get a good sketch of what's going on and use that to analyze the problem. Okay, so we have a rectangular sheet of tin. I'm going to use my finer tip pen here just so you can make sure I get everything in here sort of neatly. All right, and we're going to cut the corners out of each, or out of the rectangle. Okay. Okay, there's squares, it tells us, so that's important. We're going to cut the squares out and fold the sides up to create a box. All right, so what that means is that these dimensions all have to be the same. So that's x, 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 and x. All right, if those, the dimensions of the box then are x by x, and one side, the long side, is 25, and then the short side is 20. Okay, so if that's the case, then we need to figure out, or I think we've got enough information at this point then to get the model. But if you're still not completely convinced, we can draw this three-dimensional as well. So this will be a, you get to see my fantastic 3D art skills here. So what we'd be doing is folding up this side, this side, this side, and that side, and we would get something that looks like this. Okay, so then the question is, what are the dimensions to get the volume of the box? Because we're trying to maximize the volume, right? So we want an equation, or function, excuse me, for v of x. If we fold up the sides, then the height of this has to be x, right? The height of the box has to be x. You can label it here or here or here, it doesn't matter. And then what is this length going to be? Well, the whole side here of the rectangle is 20, but we're going to be taking off this piece here, and we'll be taking off this other piece here. So we'll be taking off two x's. And so that means that the length of this side will be 20 minus 2x. And then the question is, well, what's the length of this side here? Same kind of reasoning. It'll be 25 total minus 1x and another x with 2x's. So 25 minus 2x's. Okay? So our formula for volume then will be x. length times width times height, right? Or base times the height. So x times 20 minus 2x times 25 minus 2x. I'm sorry, I almost ran out of space there. Okay, so that's what we're going to optimize. And take a look at the graph. In fact, just to save time in the video, I'm not going to show the graph, I don't think. But if you look at the graph, you should find the maximum is at x equals 3.68 inches. So you can take a second and double check me on that. And the y coordinate there at 3.68 will be what the volume is. But this didn't ask for the volume. It just asks for how large the square should be to cut it out. So a very common mistake here is to find x when they really ask for the volume. So you want to be careful with that on multiple choice tests. But in this example, they were asking for the dimensions. Okay, so let's go to the last problem here for this video. A man wants to build a rectangular enclosure for his herd. He only has $900 to spend on the fence and wants the largest size for his money. He plans to build a pen along a river on his property, so he doesn't have to put a fence on that side of where he's trying to fence in his herd. The side of the fence parallel to the river will cost $5 per foot to build, whereas the side perpendicular to the river will cost $3 per foot. What dimensions should he choose? So this is a perfect example of a situation where it would be good to have a picture. So I'm going to sketch the river first here. So we'll go, this will be the river. Okay. Then we will take and sketch out where the fence would be. So the fence will go something like this. Like that. And it doesn't matter what you call the dimensions, really. I'm going to call this side x, I guess, and we'll call this side y. And so then the area of this would be x times y, right? So we'd have a equals x, y, okay? And what we're trying to do is maximize the area. Now, you can see that I have area equals x times y. That's two variables. And the function that I would be trying to graph, if I was to graph the function, would be a, because I'd want to maximize a, or a of x, or the function for area. So in a lot of these examples, in fact, all that we've shown here, except for, I guess, the last one, but the first two in this one, we have two unknowns. And in order to remedy that problem, we usually need to find a second equation so that we can use our techniques for two equations and two unknowns. The other information that we're given here, the other constraint, is that we can only spend $900. Okay, so that's where my other equation is going to come from. It's going to be cost. Okay, so we know this. We know that $900 is as much as we can spend. And let's just assume that we want to spend every penny of it. Okay, so $900 is going to be equal to the cost of the fence. Well, how much does it cost to build the parallel? Well, parallel to the river costs $5 per foot. Well, how much fence is over there? Well, y feet. Are we in feet? Yes. Y feet is going to be over there. So it's going to be y plus, 5y plus, and then, because it's $5 per foot, and then here it's going to be x and x. So we actually have two pieces of fence there with length x, and then that section of the fence costs $3. So we'll have $3 times however much fence there is, which would be 2x. Okay, so I've got 900 equals 5y plus 6x. All right. So two equations, two unknowns. Remember that our one equation is x times y. All right. And so what we'll do is solve this for y and drop it in there. So I get ultimately y equals 900 minus 6x divided by 5. You're going to take this, drop it in here. So here's my formula for area, my function for area, excuse me, x times 900 minus 6x divided by 5. All right, so when you get the graph of this, I think it's going to be quadratic. It's going to end up being an upside down quadratic. You'll get the maximum, the x value, in other words, this dimension that satisfies, represents the maximum the graph is going to be. And you should, by the way, you should try this graph and see if you can get the same thing. But it's going to be 75. Okay, the A value at 75 will be the area. That's not what they want, though. They want the dimensions. That's what the question is asking for. So they want to know x by y, or length by width. All right, so 75 for x, and then y. When you go plug your equation in for, or you plug in x right here, you'll get y, and it turns out to be 90 for y. So those are the dimensions that maximize the area given the cost constraints as well. All right. There's a couple other examples from optimization that we're going to talk about, but we're going to deal with those in a second video. This will be the video that kind of gets you started on the first part of the assignment. And then the next video will have the more involved optimization problems, a couple examples of those. So that wraps up the first part of 5.4.